Hello, I am Bruno SAUVALLE from in Paris. I will present our paper on unsupervised multi-object segmentation using attention and soft-argmax. The goal of the proposed model is not only to perform the unsupervised segmentation of the objects present in a scene, but also to build an object-centric representation of this scene. We'll then represent the background of the scene by a low-dimensional vector, and each object by an appearance vector, completed by the coordinate of the object, scaling values, which represent the size of the object, and activation values, which can be considered as a form of relative depth estimate and allows to manage occlusions between objects. What kind of inductive bias do we use to learn these object-centric representations? First, in order to learn the background, we assume that all the background frames in the dataset lie on a low-dimensional manifold. In order to learn the object representations, we also assume that the objects appearing in a given dataset have similar appearances but different positions and scales. The model is composed of the background model and the foreground model. The background model is simply a convolutional autoencoder, which makes sure that the reconstructed backgrounds lie on a low-dimensional manifold. The object model uses a segformer model, which generates two kinds of high-resolution outputs, one global feature map and k object attention maps, where k is the maximum number of objects present in the scene. In order to get the coordinates of the detected objects, we simply compute the spatial average of the coordinate grid weighted by the attention maps. In order to get the appearance vector, scaling values, and activation values of the objects, we proceed similarly by performing a spatial averaging of the feature map using each attention map as weights. The object latence codes are then refined by a transformer encoder. In order to decode these latent codes, we first use a convolutional glimpse generator to decode the appearance vector and get a normalized image and a mask of the object. We then use a spatial transformer network to scale and translate this glimpse at the right place in the scene. We then get k image layers for the background objects and one image layer for the background. In order to manage occlusions between these various layers, we compute for each pixel a pixel-wise layer weight and get the final image by taking the weighted average of these image layers using this pixel-wise layer weights. In order to get the segmentation, we simply assign to each pixel the layer index which corresponds to the maximum of the pixel-wise layer weights. In order to train the model, we use a L2 reconstruction loss and an auxiliary pixel entropy loss, which makes sure that only one layer is visible for each pixel in the final image, since we assume that the objects are opaque. We have observed that the baseline training scenario of the complete model may fail because of the competition between the background model and the object model to reconstruct the image. We have then implemented a curriculum training scenario. We first train the background model alone using a robust loss function. We then freeze this background model and train the object model during a second phase. We then fine-tune the background model and the object model simultaneously to get the final model. This table shows the results of the proposed model on the Clever and Clevertech datasets, which can contain up to 10 objects per scene. We observe that the proposed model significantly outperforms the state-of-the-art. This slide shows some examples of unsupervised object segmentation on the datasets Clever and Clevertech. The possible applications of the proposed model are the following. First, the model can be used to perform object instance segmentation on real-world video with complex backgrounds. Second, the object feature vectors produced by the model can be used as inputs to other models in order to perform more complex tasks, such as visual question answering or reinforcement learning. The code of the model is available on GitHub. Thank you for listening.